So let us begin lecture 17 of the course on galaxies. So last time, this is where we had stopped. We had said that there is this dropout technique that is extensively used for the identification of high redshift galaxies. And the key thing in the dropout is the two key features in using the dropout technique are the Lyman limit at 912 angstroms, below which very little flux is seen, and the Lyman alpha emission line, which is quite bright in the star forming galaxies, and therefore will give you a lot of flux in whatever filter you use there. And then, of course, for comparison, you may want to use a redder filter. So here's a little cartoon that I just made. So suppose you have this the Lyman break, and then there is the Lyman alpha forest, and then as you go on, you have this peak corresponding to the Lyman alpha line, and then you have a slow slope. The slope may be very blue in the case of quasars, which means the slope is sort of negative, but it can also be positive in a few cases. If it's not such a vigorously star-forming galaxy, you can even have a positive slope. So now suppose I have three filters which are shown, whose response curves are shown in these three red curves that you see in the figure. If you have that, how will you, with this information, how will you use the flux measurements in these three filters in order to construct a candidate list of high redshift star-forming galaxies? Okay, so that's the question that's being posed to you. Okay, so let us call this textbooks. So the first filter, let us say, is called F1. The second filter, let's say, is called F2, and the third filter is called F3. Okay, so how are you going to use the flux measurements in these filters to carry out the selection of high redshift galaxies? So first of all, what can you say for high redshift galaxies? What will be the value of F1 minus F2? Okay, these are magnitudes in the F1 filter and magnitudes in the F2 filter. What will be the value here? And similarly, what is going to be the value of F2 minus F3? Sorry? Louder. Correct. Right. Huh? Yeah. You're considering magnitudes only. So these are like colors. So I mean, instead of F1, F2, if I said U filter, B filter, and V filter, U minus B will be negative. Yes, so but you are doing U minus B. So B has a smaller nominal value of the magnitude, correct? No, higher nominal because it's fainter. No, sorry, wait, what are we doing? U minus B, U has a lower flux and B has a higher flux. So what will be the value of U minus B? It will be positive, correct? It's not negative, it's going to be positive, correct? Huh? So it's going to be red in this filter. Sorry, blue in the red in this filter, correct? Because the redder band has a higher flux. But if you compare this filter F2 minus F3, what will it be? negative. So it's going to be blue in that filter, right? So if you use this kind of criterion, then you are able to separate galaxies. So if you make a color diagram, which is commonly done in astronomy, you will find that these objects, this particular thing is quite red, and this particular color is quite blue. Right. So that is what is used. So back to our thing. It was first extensively applied in 1996. Okay. So this is a quick review question. A galaxy has U minus B of minus 0.2, another has U minus B of 0.1. Which is redder? First one is bluer. Second one is redder. Correct. Okay. Because always, another thing to remember is that whenever you write color in this font, you always write the shorter wavelength filter on the left hand side. U minus B, B minus V. You never do V minus B. Okay. You do R minus K, but never K minus R. That's just the convention. So that you know that a negative value will correspond to a bluer color in that filter, and a positive value will correspond to a redder filter. Yes. I think that's there. Yeah. So now what has been done here is that one takes a spectrum of a typical elliptical galaxy, SB galaxy, SC galaxy, and so on, and computes the color by placing this galaxy at different redshifts. So you take a 0 redshift typical elliptical galaxy and place it at different redshifts and see how its color changes. Okay, why does the color change? The spectrum shifts. Okay, this is not an evolution. The spectrum itself is not changing, but there is a stretch and a shift happening because of the redshift. Right, the whole spectrum is moving and stretching also. So what this shows is a track of elliptical galaxy spectrum as a function of redshift. So this is at redshift 2.8. This is at redshift 3.5. Okay, so it's increasing like this. Right, so the elliptical comes in like this and goes in like this. So suppose you make a wedge. Suppose you say that I'll select all galaxies which lie in this region of color space. Right? What will happen? You will pick up all galaxies which lie between, say, redshift 2.8, 2.9 to redshift 3.5 or maybe 3.6. Right? In whatever galaxy lies in that redshift range, you will pick up. Will you pick up all morphologies? All the curves are nearly coincident. Okay, so you'll pick up all morphologies. Okay, but remember, morphologies is probably a wrong proxy, but you will pick up galaxies with different star formation situations. Because remember, morphology doesn't exist. There are no grand design spirals at redshift 2.8, etc. But there are galaxies that are star forming like spirals, or there are galaxies that are quiescent like ellipticals at these high redshifts also. So you will pick up essentially all kinds of galaxies with a bias towards star forming. And we'll see that in a minute. So notice here that U minus G color is higher than some threshold. So it's red. And G minus R color is below some threshold, which means it's blue. Right? Blue word of that threshold. Okay. Yeah. Which one? This one? Huh? That's at low redshift. That's just the spectrum where the spectrum of the elliptical galaxy peaks. Okay. So that is related to where it moves in the U minus G versus G minus R bands. So here it is becoming bluer and bluer in the U minus G band because of the way the spectrum is, the curvature of the spectrum in that band as it redshifts. These are all very low redshifts. Okay. So U band dropouts. So this is what it will practically look like. So you see here in the near UV filter, U band filter or something, you will not see the galaxy at all, because there you are sampling the rest frame spectrum shortward of the Lyman limit. So no flux. So the galaxy is not visible. It is visible in green, it is visible in red bands. So if you plot it on the color plot that we just saw, it will lie within that wedge, and this will be a candidate high redshift galaxy. It's called a U-band dropout. So U-band dropouts are typically at redshift 3, B-band dropouts are at redshift 4.5, and the radar filters will generate dropouts at higher redshifts. So now this is an actual image taken with the keck, and what is shown with blue circles over here are candidate high redshift galaxies. So there are so many of them. Black spots are stars. These are stars. These big black spots are all stars. The fainter objects are galaxies, most of them. The LBG candidate density in this particular plot is 1 galaxy per arc minute square. So this is a pretty big field of view. But you can see there are lots and lots of candidates. Now, this whole study of LBGs started only in the 1990s. It was not possible to do it before that because of two technological developments. First technological development was large format, high quality CCDs became available in the 1990s. So you could place a large CCD at the prime, at the focal plane of your instrument and get images of thousands of galaxies in one shot. One image will have a large field of view and will contain thousands of galaxies. That is one. The second important innovative development that happened was, for the first time, we had multi-object spectrographs becoming available. Before that, we didn't do optical fiber-based spectrographs. We did slit-based spectrographs, wherein you had opening a slit, light was read through, and you obtained a spectrum. So there you were restricted. You could move the slit, you could turn the slit around in different directions, but you could get basically a spectrum of one galaxy at a time. A 1D spectrum or a 2D spectrum in that case, but a one galaxy at a time. Now, for the first time, because of you could put optical fibers at each of these galaxy positions, you could get spectra of hundreds of galaxies in one go. And that kind of multiplexing increased your efficiency by that factor. So you became 100 times more efficient, because instead of getting one galaxy spectrum, you are getting 100 galaxy spectrum all at once. So both of these developments enabled a dramatic improvement in the study of, first in the identification and confirmation of Lyman break galaxies, but also in their subsequent study. We couldn't have done this. So what Chuck Steidel and his collaborators were able to do in 1 year, in 95, 96, people had not achieved in the previous 50 years in terms of identifying high redshift galaxies. Just totally changed the game. So here are two examples of high redshift galaxies, two dropouts. One is at 3.2, one is at 3.5, etc., and various lines, etc., are identified here. And what they're compared with is NGC 4214, which is a galaxy which is a dwarf irregular galaxy in the nearby universe. And the reason this is done, because we expect naively that these galaxies which are at high redshifts cannot be high mass galaxies. They have to be low mass. And why did we pick a irregular to compare to? Because we know that these are likely to be star forming galaxies, and in the local universe, small star forming galaxies are the dwarf irregulars. So that is why the comparison is done with an irregular galaxy. But that's how you do it. It's not that high. They're very local. They're very close by. No, this spectrum is redshifted. So as you can see, there's the Lyman alpha line is shown somewhere and so on. So this is the observed spectrum for the high redshift galaxy. And the low redshift galaxy spectrum has been stretched and shifted to that redshift. Yeah. So, but these are not, see, Lyman alpha should be at 1216 angstroms. It is showing at 5000 plus angstroms. So obviously it's a redshifted line. Yeah. So now that you know those U-band dropouts, you can image them. You can look at them with the Hubble Space Telescope. These are very distant galaxies, very, very faint, very, very small in size. And therefore, the sensitivity and more importantly, the high diffraction limited resolution of the HST is quite critical to studying them. And as you can see, morphologically, they are, I mean, they're like irregular galaxies. There is no spiral structure. There is no elliptical like smooth structure. Some of them are like sort of broken up. I mean, it seems as if there is star formation in two patches of the galaxy. Maybe these are merging objects also, like two small star forming galaxies are very close to each other. Here you see a almost linear structure. Here you see different kinds of structure. The only thing that is common across all of them is their color. Okay? They look sort of greenish or greenish blue in color, and that is because of the filters we have chosen. They seem to be brightest in the middle filter. So they look green because we have mapped blue to the bluest filter, green to the next filter, and red to the third most. Because the Lyman alpha is sitting in the green filter, that is why they are all looking sort of greenish in color. Right. So it became possible suddenly in the 1990s to identify these objects. Within a few years, between say 95 and 2000, thousands of galaxies at redshift 3 had been identified. Okay. So LBG color selection is biased strongly towards star-forming galaxies at high redshift. Why is that? So in your, suppose you have filter 1, filter 2, filter 3. In this technique, where will the flux be highest? By our selection criteria, filter 2. Filter 2 is where the flux is highest. And why is it highest? That is what part of the res frame spectrum is it sampling? I mean, why are these galaxies green? Sorry? No, there's this is, don't take these colors literally. We have just mapped this is not that the galaxy, if you go close to it, is going to look green in color. Not at all. Okay. It's going to look very blue in color because it's going to be highly star forming. Because of high redshift, it has redshifted and it's looking green to us. Fine. Fair enough. So, but why are we picking up star forming galaxies more than others? Because of Lyman alpha. See, Lyman alpha is sitting in your middle filter. Okay. If the Lyman alpha is quite prominent, which means there is the galaxy strongly star forming, then you are more likely to pick it up in your color space. So that is why it's a known selection function. Any other reason why you would pick up star forming galaxies? Yes, correct. So a lot of galaxies there are going to be star forming because they are at high redshift. They have not yet built up the stellar mass. So they are in the process of building up the stellar mass, increasing the star. So they are star forming. These galaxies are what are called star burst galaxies, which means they are undergoing a burst of star formation, very, very high star formation rates. Okay. Do you expect these star forming galaxies to be strongly clustered? No or yes? Where is star formation happening in the early universe? Yesterday we looked at that video. Huh? Intersecting, yes. And today, what is that region today? They are clusters. Okay. So will they be, so clusters are clustered, right? Obviously, by definition. At high redshift, they were also the most clustered things. So we are going to preferentially pick up galaxies that today lie in clusters. So the progenitors of galaxies at the cores of clusters are the Lyman break galaxies at high redshift. So they will be clustered, no doubt they will be strongly clustered. This has been measured, and but that clustering allows you to do one more thing, which is these are very rare objects. They correspond to high mass dark matter halos, right? These are the most luminous galaxies at that redshift, right? So we are doing a color cut, but also we are having a flux limit. So we will have a Malmquist bias. So we will only pick up at redshift 3 the most luminous galaxies at that redshift, not low luminosity. So they will naturally correspond to high mass dark matter halos. So what can you do? You can measure the clustering. You can measure the correlation function of Lyman break galaxies at redshift 3. Okay, and find out what is your, we remember it's a power law with the characteristic slope and a characteristic R0. Measure the R0. Compare the observed correlation of R0, of the correlation length R0, with numerical simulations of dark matter halos. And then you will be able to say, okay, these Lyman break galaxies are all lying in these kind of halos. Okay. And therefore, you can then determine the characteristic halo mass of Lyman break galaxies. And that comes out to typically 3 into 10 raised to 11 solar masses at redshift 3, and somewhat higher masses at redshift 2, 10 raised to 12 solar masses. The correlation length is observed to increase with the luminosity of the LBG, indicating that more luminous Lyman break galaxies are hosted by more massive halos, which are more strongly biased, which means they're more strongly clustered than less massive ones. Okay, so that also you can verify. And the only reason you can do this is because you have thousands of galaxies, one galaxy per arc minute square. So if you do 1 square degree observation, you get 3,600 galaxies all in one shot. And nowadays they do even better than that. So we have higher density measurements of the Lyman break galaxies. If we had identified one galaxy here and another galaxy there, we couldn't have measured correlation length. We couldn't have done anything of this sort. But because we are doing this, and because because a galaxy has to lie inside a dark matter halo, and once it is in a dark matter halo, it can only get into another dark matter halo if its halo merges with that dark matter halo, right? The dark matter halo has such strong gravitational potential. Galaxy cannot say that I don't like this dark matter halo, I'll move to an adjacent halo. It simply cannot do that. So because of this biasing, and because by measuring correlation function of the Lyman break galaxies, we are able to measure their clustering, and we are also able to measure the halos in which they're sitting. Now we can go further. We can say that, okay, at redshift 3, this halo was there, halo number 75, where I will look at the halo merger tree of that particular halo and say that at redshift 0, which halo is it corresponding to, right? Halos are merging, galaxies are merging, everything is merging. But you can trace it back in the simulation very easily. And then you can say that, okay, what is the mass of the halo at redshift 0, where these Lyman break galaxies are sitting today? And then what kind of galaxies sit in such massive halos today? And there you get. So if these results are combined with the observed correlation functions of galaxies in the local universe at redshift 1 and so on, and with the help of these numerical simulations to guide you to how the dark matter halos are merging, then this indicates that a typical high redshift LBG will revolve into a elliptical galaxy today. LBGs also lie at the centers of protoclusters, and therefore they will lie today in the most massive clusters. So the CD galaxies, which are these big elliptical galaxies which sit at the centers of most of the clusters in the local universe, their progenitors are the LBGs. Okay. So now this word progenitor, one should be a little cautious. I don't want to cause a lot of confusion. Remember, you see one galaxy there in the background and you see a cluster in the foreground. Doesn't mean it's the same galaxy. Can't be, right? Because speed of light is finite, but the speed of galaxy cannot be greater than the speed of light. So it's not the same galaxy. So don't think of that this galaxy's parent is that galaxy. What it means is I see a galaxy here, and I see another galaxy at high redshift. This galaxy had a parent which was very similar to the high redshift galaxy which I have seen. So progenitor means it's a class progenitor, not individual object. It's not as if that progenitor galaxy gave birth to this galaxy. No, they're different objects. The LBGs are vigorously star forming. Okay, by vigorously star forming, one means hundreds of solar masses getting created per year. For comparison, if you take the Milky Way, which is a reasonably large and reasonably highly star forming galaxy in the local universe, we are at about 3 solar masses per year. This is could be at 300, in a few cases at 1000 or 2000 solar masses per year. This also tells you, suppose a galaxy is at 1000 solar masses per year, how much mass will it build up in a gigayear? Hmm? 10 raised to, in a gigayear, if it sustains this 10 raised to 12 solar masses. Okay, and we hardly have any galaxies like that. Our galaxy, which is pretty massive, is a few times 10 raised to 11. So you can, within a gigayear, which is 1/10 of the lifetime of the universe, within a gigayear, we can build up extremely massive objects by just doing this, by building them at 1000 solar masses per year. But when that happens, if you're building at 1000 solar masses per year, you're also going to produce a lot of high mass stars. These high mass stars drive very strong stellar winds. So they're losing mass at a very high rate. And in addition to that, your supernova rate will also be higher. If you go from 3 solar masses per year to 1000 solar masses per year, your supernova rate in your galaxy will be correspondingly higher by the same factor, correct? Assuming the same IMF will be that much larger. So these drive very, very powerful galactic winds. So there are all kinds of outflows that are seen from Lyman break galaxies. And how do we detect such outflows? In radio you can detect, but also in the optical you can detect. What will these outflows produce? In terms of lines, emission is rarer, but it can produce absorption. There's gas flowing out at very high speeds. It can, so you will produce absorption by gas at a redshift which is very close to that, but which has a high peculiar velocity. So there'll be some gas flowing in your direction, there'll be some gas flowing in opposite direction. Both of these will produce absorption lines. One of them will be quite a little bit blue shifted with respect to the spectrum of the quasar of the star forming galaxy, and one will be redshifted and so on. So these kind of high speed outflows, means high speed measured as related by their Doppler shift, peculiar Doppler shift relative to the Lyman break galaxy, have been seen and measured in several galaxies. Correct. Correct. So what we said earlier is probably not correct. That it is not true that Lyman break galaxies will have sustained high star formation for a gigayear. That assumption is probably wrong. So that what you're saying is absolutely right. This will disrupt the star formation. Okay. But sometimes what can happen is, maybe what is also happening is these high star formation is producing feedback that tends to reduce the star formation. But maybe mergers are happening. While these things are happening, two more galaxies are falling in, gas-rich galaxies are falling into this galaxy. So that merger process is enhancing the star formation. So it is to be thought of as not as isolated objects star forming on their own, but objects that are undergoing a large number of mergers. And with HST, that also has been seen. So you see these Lyman break galaxies and find the probability of finding another Lyman break galaxy very close to it at sort of merger distance. Same redshift and about to merge. That is also very high. We don't have such galaxies in the local area. Yes. Correct. Yes, it is. It is, so long as your high star formation rate doesn't last for too long. Okay, somewhat less than a gigayear, maybe less than half a gigayear or so. Yes, you can build up. So you don't want to overshoot, but you don't want to undershoot also. You don't want to predict galaxies of 10 raised to 13 stellar mass, solar masses in terms of stellar mass, because they don't exist. At the same time, you don't want to under predict the number of 10 raised to 11 solar mass galaxies or 10 raised to 10 solar mass galaxies. So it's consistent, yes. In the radio, you won't have the sensitivity to find it at these redshifts. We are finding relics in relatively nearby clusters, shock relics, but it's quite hard to find them at this redshift. Maybe with SK we will have sufficient sensitivity to see them, but with current generation radio telescopes, not. Yeah. They are a few times 10 raised to 11 up to 10 raised to 12. So for those galaxies, if you wanted to form all their stars within a gigayear, you would need 1,000 solar masses per year. But remember, the growing stellar mass, star formation is not the only way to grow your stellar mass. Mergers is another way to grow your stellar mass, correct? Dry mergers. So what we know for a fact is that with these massive CD galaxies at the cores of clusters, they have grown partially by being vigorously star forming early in their lifetime, and partially by undergoing a number of mergers through their lifetime. So both have contributed. Second generation star formation, where? Yes. 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 So they can grow with time. It's not as if they form. But what happens is this process is so vigorous. There are no local analogs. Don't try to look for local universe analogs of galaxies forming 500 solar masses per year. There are none. Who said they've stopped forming? Uh, yes. Yeah. Yes. Yeah. No, but mergers are also happening. Like I said, when this is happening, in fact, this is a case of a M82. This is a nearby galaxy with strong galactic winds. This is a merger case also. So it's driving winds, vigorously star forming, dusty. So yes, so it can be just a gas-rich merger with a gas-rich galaxy. Immediately it starts. Yeah, that is correct. Okay. So now, just like you have the Lyman break, there is also something known as the 4000 angstrom break. Uh, at if you have a lot of evolved stars, which means stars which are at least 1 giga-year old, right? Then in the outer atmospheres of these stars, there are certain, there is an increased opacity at wavelengths longer than, shorter than 4000 angstroms. So what that causes is that it causes the spectrum to dip at about 4000 angstroms. And this is only seen if you have a dominant population which is older than a giga-year. This is referred to as the 4000 angstrom break. Okay? So it is like your Lyman break, but it is not so strong, not so severe. It's much milder. And it is only seen in a galaxy with a greater than 1 giga-year stellar population. So if you look at today's elliptical galaxies, they qualify, almost all of them qualify. And therefore, elliptical galaxies do show a strong 4000 angstrom break. But if you take local spirals, then those spirals will not show that 4000 angstrom break. So if you place your GRI filter like this, again, you can come up with a color space that will help you detect the 4000 angstrom break. So this kind of selection technique will obviously likely to find galaxies with an evolved stellar population. Okay, I use ellipticals as an example, but that's only in the local university. The morphology may not be elliptical, but these are galaxies with an older stellar population. And so you can find galaxies at redshift 1. But if you look for this kind of Lyman break galaxies at low redshift, you can't find them. Why is that? So we are actually able to find galaxies at redshift 3 more easily than we can find them at redshift 1.5. So why? So this is referred to as the redshift desert. Between roughly redshift 1 to redshift 2, we don't know of enough galaxies. Obviously they exist, but we have not been able to find them. We have found lots of galaxies at redshift 3, 4, 5, and so on, but not yet. Let me put it that way, you find no galaxies, virtually no galaxies between redshifted 1 and 2. Red frame is different. That's the clue. So what? So can you expand on that? So where will be the Lyman alpha emission for a redshift 1 galaxy? (2400 angstroms). Which band is that in? It's in the ultraviolet. So unless you have a telescope which is sensitive at ultraviolet, and you want to go to Lyman limit also, which is at 1800 angstrom for a galaxy. So you will have to have a UV telescope, UV imaging telescope to first select your candidates, and then you will have to have a UV spectrograph to confirm the Lyman alpha line and other lines. Maybe you don't really need a spectrograph because you can get the spectrum via some other lines in the optical. That is not a crucial requirement, but you need a wide field ultraviolet imaging telescope, which is also sensitive. We have something like UVIT and things like that, but it's not sensitive enough to find galaxies at redshift 1. That is why we don't have knowledge about what is the. So we know a lot about the local universe and nearby galaxies. We know a lot about the high redshift galaxies, but intermediate redshift galaxies we know very little at the present time. No. Okay. So yeah. First of all, at those wavelengths, you have to be in space. Okay, you have to have a space telescope. So that already makes it quite expensive. And secondly, UV detectors are very difficult to build. The technology is not that advanced as it is for optical or even for infrared. Okay, but I mean, little bit you can do at very low redshift can be find vigorously star-forming galaxies. So there is this Galaxies space telescope, small telescope, not the kind of sensitivity that will allow you to find. It's comparable to UVIT in terms of its size. They've found two populations of low redshift star-forming galaxy. One compact population corresponding to high Z Lyman break galaxies, and a non-compact star forming population of large disk galaxies. Right? So there are two populations. So these compact population of star forming galaxies are probably like dwarf, vigorously forming star forming dwarf irregulars. And the disk galaxies, that population we already know, which is basically Milky Way, Andromeda type large disk galaxies, which will also show up in the UV surveys. But we don't have the sensitivity to go to redshift 1 with these instruments. Right. But we can go in the other direction, no problem. We can go and find Lyman break galaxies at redshift 6 if you want. So these are going to be, so these are U dropouts, of course, but also B dropouts, also V dropouts, also R dropouts, I dropouts. In Z, you can begin to see something. And once you go into the near infrared, you begin to see the galaxy. Then in J band, H band, K band, etc., you can see it. But you can't see it in any optical band. It's a high redshift Lyman break galaxy at redshift 5.74. So the search for Lyman break galaxies has used two sort of ways. One is where you do a wide area survey with a telescope like Keck, observe many square degrees of sky, identify candidate high redshift galaxies, obtain spectra for each of them using your multi-object spectrograph, confirm it. But some people have gone and said, no, let's go deep, but in a smaller area. So there have been a number of surveys with the Hubble Space Telescope. These have been, so the original one was something called Hubble Deep Field North. Then they did Hubble Deep Field South. Then they did Hubble Ultra Deep Field. And then they did many small area surveys with called Goods, Gems, Cosmos, Candles, etc. So there have been a slew of surveys with the HST, one of whose goals was to find these very high redshift galaxies. They use the ergodic principle again that we can use the. Now this is a plot for the WMAP9 cosmology of the look back time in gigayears. Okay. So by the time you go to redshift 2, your look back time is already just above 10 gigayears. So the universe is 13.7 gigayears old. We are looking back 10 gigayears into the past already at redshift 2. By redshift 6, we have gone to about more than 12 gigayears. So we are approaching the first gigayear after the Big Bang by redshift 6. So one can really go back quite a long way in the history of galaxies and trace them. So this is the Hubble Ultra Deep Field. More than 10,000 galaxies are there in this single image with the advanced camera for surveys. Of course, you have to do it in many filters. If you do it in many filters, then you can use different filters and different color combinations to, in one shot, identify candidates at redshift 3, at redshift 4, redshift 5, 6, 7, and so on. And all of that has been done, and a lot of high redshift objects have been found there. If you look at their stellar populations of these Lyman high, z equal to 6 Lyman break galaxies, they seem to have stellar populations with masses and lifetimes comparable to those at z of 3. Right? This implies that at a time when the universe was only 1 gigayear old, a stellar population with mass of 3 into 10 raised to 10 solar masses and age of few hundred million years, as indicated by the relatively weak 4,000 angstrom break, was already in place. So this is now beginning to pose problems for our understanding of the universe, because we are finding galaxies with a very high mass at very high redshift, which means the universe was very young. How did the universe build up so much of stellar mass in such a short time? You can measure the metallicity, and you can find high metallicity gas in these sources, also indicating that it seems to have formed stars very quickly. These objects are very compact with half-light radii of 1 kiloparsec, very small. The Milky Way has much larger half-light radius, and thus differs substantially from the galaxies population known in the low redshift universe. So LBGs are obviously very faint. Is there some geometric configuration that will make their detection easier, or that actually makes their detection easier? Huh? Meaning their shape, size, etc. So shape is probably not that relevant. What about size? Yes. So if you have two galaxies, both at redshift 3, both forming stars at 300 solar masses per year, okay, so one which is compact, another which is more diffuse. Which one will you be able to detect? The compact. So the fact that we see many of them are compact, uh, one has to be treated with a bit of caution, because we may just, because of our detection technique, we are not finding the non-compact ones. We can't find them. What do you mean by which is corresponding to which? Yes, they will naturally be lower metallicity than in the local universe. That is correct. Distinct, but you don't detect them. They just don't appear in your sample. If you have a diffuse galaxy, it is just not bright enough to go above your flux limit, because you also have a surface brightness limit, not just a total flux limit. Right. Okay. So now you can ask the questions. Okay, these are some unusual objects. Are there any normal galaxies at redshift 3? By normal, one means a galaxy which looks normal and is not forming stars at this ridiculous level. And is it possible to see such galaxies? So they found one. There is a lensing cluster at redshift of 0.37, background galaxy at 2.72. Okay, this is the most distant normal galaxy known, and we only found it because the magnification is 30. So it is 30 times brighter than its inherent brightness. And this sort of very fortunate coincidence allowed us to find these galaxies. But since not enough have been found, we don't know anything about their statistics. I mean, are there any galaxies at redshift 3 which are not star forming? We don't know. Sorry? Yeah. No. It's a galaxy cluster. Galaxy cluster. So, the one which is lensed. This one. The white looking object is the normal, meaning in terms of star formation. Okay, it is not vigorously star forming. Of course, it's not a very big object or anything, but it's yeah, not in terms of morphology. Morphology has no meaning beyond redshift 1, but in terms of its star formation rate. To learn more about Lyman break galaxies, there is a very nice review by Giavalisco et al. In 2002. That was the time when everybody was wanting to study Lyman break galaxies. So there was an annual, so ARAA is the annual review in astronomy and astrophysics, which are these long articles which are published in every year in the form of a book. It's a sort of hardbound book, blue in color. You can find it in our libraries. Okay. So these objects, we said, these Lyman break galaxies, they are what are called starburst galaxies. Milky Way is forming stars at 3 solar masses per year. Starburst rates is more than a factor of 100 higher. But so if there is any dust, will there be dust? For sure, we don't know, because it depends on the metallicity. Only when the metallicity is higher than some threshold value will you begin to get large amounts of dust. But we know that there was a lot of vigorous star formation in the early lifetime of the galaxy, lots of rapid buildup of stellar mass, and therefore at least there must be some galaxies which are dusty. So if such galaxies exist, so these are like Lyman break galaxies, but Lyman break galaxies have to be relatively dust free, because only then will the Lyman alpha photons, etc., be able to escape. So we cannot detect very dusty galaxies using the Lyman break technique. But do they exist? And if they exist, how can we detect them? So the dust heated by these hot stars radiates in the far infrared, rendering these starburst galaxies very strong far infrared emitters. So we launched a far infrared telescope in the 1980s, which was called IRAS, Space Telescope, and that discovered a lot of far infrared luminous galaxies. These were distant galaxies, but they were still bright in the far infrared because they were vigorously star forming and dusty. So that gave, so first you called them IRAS galaxies, but somebody said don't call them IRAS galaxies. You call them by some more physically meaningful term. So they called them ultra luminous infrared galaxies. And then people said there are some which are not that luminous. So there are also LIRGs, luminous infrared galaxies, so which are about an order of magnitude less luminous than ULIRGs, but extremely, yeah. Yes. So, but because far infrared band goes from 25 microns to 750 microns. So even if it shifts, it still remains somewhere in the far infrared band. So you're right, it shifts, but some of them you'll be able to look at with JWST, but JWST is not a far infrared telescope. So only if these dusty galaxies have very hot dust, large amounts of very hot dust will you be able to detect it with JWST. But if they are cold, warm dust or cold dust, that is too far away for JWST to observe. Yeah. These things are characterized by what is called as a negative K correction. So what does that mean? So this is a nearby dusty galaxy, vigorously star forming, R220. What they've done is they've taken the spectrum of R220 and they have redshifted it from some low value out to some high value. And at high wavelengths, the spectrum is such that it has what is called as a negative K correction. Okay. Do you people understand what is meant by K correction? Yeah. And normally the K correction term is a positive number, so some magnitude, so many magnitude. Here it has a negative K correction. What is the implication of that? It will be more bright at high redshift. More because the flux density will be higher at redshift. So because of that, one is able to detect them. So let us say, take the last 3, 4 objects, 6, 7, 8, etc. You can detect them even if it is at redshift 8. You may be able to detect it more easily at higher redshift than at lower redshift. Okay. Of course, the overall flux goes down. So this is an dominant effect. But here they're very close. So the negative K correction allows you to detect these galaxies at very, very high redshift in the far infrared. So their far infrared luminosity doesn't drop very much. Yes. So this is an example of a dusty star forming galaxy in the nearby universe. Okay. So this is called as the antennae, and each knot, which means each of these sort of dense star forming regions, is 10⁵ solar masses. So it's not 1 or 2 stars, there is 10⁵ stars in each of those knots. So pretty vigorously star forming. And when you have that, you see both blue supergiants and red supergiants. The blue supergiants are very massive stars which are at the extreme left end of the main sequence. They're very blue in color, but very luminous. Then to the right, the top right of the HR diagram are your red supergiants, which are evolved stars of lower mass, but which have gone. And both of these can be seen. So if you observe in a sort of blue filter, you'll pick up so I think this is HST with the blue channel and the red channel of the wide field camera 3. And then you can see those red supergiants in the same region. Now there are some regions which are obviously dusty, right? You don't see much, but does that mean there is no stars forming there? No, they could be forming there and they could be emitting infrared. So what this plot shows is the same image, but now we are over plotting the contours of the far infrared emission from this galaxy. And you can see that the regions which are dark, I mean this region, for example, is quite brightly emitting in the far infrared. So they definitely are star forming, and within one galaxy we are seeing examples of star formation which is relatively less dust obscured, which means region like this, and also regions like this, which is very highly dust obscured. So both kinds of objects exist. I think we can stop now and take questions and then continue next time. Sorry? Oh, it's a merger. Okay, it's a merger of two gas-rich galaxies. So, for example, your Andromeda and Milky Way merger will look like this. So there are two galaxies. This is one galaxy over here, and this is one galaxy over here. Sorry? No, the negative K correction is only if it is totally obscured. So here it's a mix. I mean, you have both unobscured and obscured dust formation. So the K correction may be slightly affected. It won't become negative, but it may become slightly less positive because you have one component like this. The red giants are not seen in this dusty region also because it's too dusty. Even red giants, the red colored stars are getting obscured. So it's only far infrared current. No, I don't think there is much segregation. So the red giants are seen here, their blue stars are also seen here. So it's not as if where blue stars are formed, red stars are not formed. The full IMF gets formed, and then some of them turn into blue giants and some of them turn into red. So this is probably not a very good analogy for the Lyman break galaxies because these are very massive objects. These are two big galaxies merging. The Lyman break galaxies, think of them as very small, compact, vigorously star-forming objects, which have no true analogs in the local universe. I mean, we have analogs. If you take your dwarf irregulars, they match the Lyman break galaxies in terms of their size. but their star formation rate is 100 times or 1,000 times lower. Yes. You can. One of the ways in which you can do it better with quasars. So, so there is something known as the Gunn-Peterson trough. So if you begin to see the neutral absorption by neutral hydrogen, then the Gunn-Peterson trough should appear in the UV spectrum of these distant quasars. And we have seen it in a few cases. But these things are still just sampling the end of the reionization, not the beginning. So for beginning, you need much more sensitivity, and that JWST will provide. So the end of reionization we are seeing, no doubt. But the beginning of reionization, if you want to see, you have to see the first stars, which JWST will do. They are more likely to be the progenitors of the high entropy systems in the local universe. So the Lyman break galaxies are more likely to evolve into present day massive ellipticals, much less likely to be the progenitors of spirals. Highly clustered region, and not even field ellipticals, but ellipticals in the central region of clusters. The Lyman break galaxies are those. One has not seen the progenitors of spiral galaxies, but going, I mean, if you look at the build-up of stellar mass as a function of time for these two kinds of galaxies, in elliptical galaxies, the build-up is very, very rapid initially, and then it slows down quite a lot. Whereas spirals, you can think of as objects that are continuously forming stars throughout their history. So then star formation rate was never very high, but it was never very low. So over 10 gigayears, they have built up their stellar mass. So therefore, they are much harder to detect the progenitors. I mean, we are detecting these because they're vigorously star forming. If they were not,